For over 60 years, we've searched for alien civilizations, mostly by listening, pointing radio dishes at the stars, straining to hear a deliberate message. And we've heard nothing. But there's another way to find them, and it doesn't require anyone trying to talk to us at all. Instead of listening for a whisper, you watch for something far stranger. A star that someone is taking apart. A star wrapped piece by piece in an artificial shell of machinery so vast it swallows nearly all the starlight, and quietly glows in the infrared like a dying coal. This is the Dyson sphere, the ultimate power plant, a structure so enormous it surrounds an entire sun. And here's what makes it more than science fiction. It's one of the few megastructures that breaks no laws of physics. We could, in principle, start building one within a century or two. Advanced aliens may have already built them. And right now, astronomers are seriously scanning the sky for their heat signatures and have found a handful of genuinely puzzling candidates. So today we're going to unpack the whole idea. Why a civilization would build one, what it would actually look like, how you'd construct something that big, and how we're hunting for them across the galaxy. The truth is weirder and more real than the name suggests. Let's get into it. Start with the why, because the Dyson sphere is, at its heart, an answer to a single, relentless problem: energy. Every civilization that grows needs more power. We've gone from firewood to coal to oil to nuclear, and our hunger only climbs. Now extend that trend for centuries or millennia. A civilization that keeps growing will eventually want more energy than its entire planet can possibly provide. So where do you turn? You look up. Because sitting right there, in the middle of your solar system, is a fusion reactor that's been running for billions of years and will run for billions more. Your star. The catch is that a planet like Earth intercepts only about 1 part in 2 billion of the sun's total output. The overwhelming majority of all that energy just streams off into empty space, wasted forever. And the Dyson sphere is the audacious solution. Stop wasting it. Surround the star. Capture all of it. It's worth dwelling on just how relentless the logic of energy growth is, because it's the engine behind the whole idea. For most of human history, energy use crept up slowly. Then, with industrialization, it exploded. And across the last couple of centuries, humanity's total energy consumption has climbed staggeringly, roughly doubling and doubling again over generations. If any civilization keeps growing its energy use even modestly, just a couple of % a year, the compounding becomes absurd over cosmic timescales. Within mere thousands of years, a steadily growing civilization would need to capture not just its planet's energy, but a sizable fraction of its entire star's output. In other words, a Dyson sphere isn't an exotic luxury. For any long-lived, growing civilization, something like it may be close to inevitable. Run the math forward far enough, and you either stop growing or you go to the star. That's why physicists take the concept seriously as a likely stage in the life of any advanced species, and why, if the galaxy is old and full of civilizations, some of them should have reached this stage long ago. To put numbers on this leap, scientists use the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. It ranks civilizations by how much energy they command. A Type 1 civilization harnesses all the energy available on its home planet, all the sunlight hitting it, all its winds and tides and geothermal heat. We're not even there yet. We're estimated at around 0.7 on this scale, still scrabbling around below Type 1. A Type 2 civilization harnesses the entire energy output of its star, and that is exactly what a Dyson sphere represents. And a Type 3 civilization commands the energy of an entire galaxy, hundreds of billions of stars. The jump from where we are to Type 2 is staggering. A star like the Sun pours out around 400 trillion watts. That's a 4 followed by 26 zeros every single second. Capturing even a fraction of that would give a civilization more power than it could ever conceivably spend. The Dyson sphere is the engineering project that graduates a species from planet dwellers to star harnessers. And here's the genuinely startling part. We are not as far from being able to start as you might think. The physics is understood. The basic engineering, solar collectors, robotic mining, beaming power, already exists in primitive form. What we lack is scale, automation, and the will. Some thinkers argue that with self-replicating robots and a serious commitment, humanity could begin a Dyson swarm within the next century or two, and have a meaningful first phase running within decades of starting. That doesn't mean we will. It would be the largest project our species has ever attempted by a factor of billions. And it raises every question imaginable about cost, motivation, and whether we'd survive long enough to finish. But it's worth sitting with the fact that the Dyson sphere isn't a far future fantasy requiring magic. It's something a civilization only modestly more advanced than ours could plausibly begin. Which means, if we can imagine starting one, older civilizations out there may have finished theirs long ago. Now, where did this idea come from? It's named after the physicist Freeman Dyson, who laid it out in a famous 1960 scientific paper with a wonderfully dry title, Search for Artificial Stellar Sources of Infrared Radiation. But Dyson himself was always honest that he borrowed the concept. The real origin is science fiction, specifically the 1937 novel Star Maker by Olaf Stapledon, which contains a brief, visionary mention of a civilization enclosing its stars to capture their energy. Dyson read it and turned that throwaway idea into rigorous physics. And crucially, his paper wasn't really a blueprint for building one. Dyson's genius move was different. He argued that if such structures exist out there, we could detect them. That reframing from could we build it to could we find one someone else built is what made the Dyson sphere a tool for hunting alien life, not just a fantasy. And the idea took on a life of its own in popular culture, which is partly why it feels so familiar. After Dyson's paper, science fiction ran with it relentlessly. One of the most famous depictions came in an episode of Star Trek: The Next Generation, which featured a complete solid shell around a star, cementing in the public mind exactly the version of the Dyson sphere that, ironically, is the least physically plausible. Author Larry Niven built an entire acclaimed novel, Ringworld, around a related but smaller idea. Not a full sphere, but a vast ring encircling a star, spun for artificial gravity. From video games to novels to films, the image of a star wrapped in artificial structure became a shorthand for unimaginably advanced civilization. The downside is that most of these portrayals show the solid shell, reinforcing the misconception. The upside is that the Dyson sphere became one of the rare pieces of hard physics that almost everyone has in some form already pictured. But before we go further, we have to clear up the single biggest misconception about Dyson spheres. One baked right into the name and into 1,000 sci-fi illustrations. When most people picture a Dyson sphere, they imagine a solid, continuous shell, a giant metal ball completely enclosing the star with the civilization living on the inside surface. It's a striking image. It's also almost certainly impossible, and Dyson himself never meant that. Here's the problem with a solid shell. A rigid sphere around a star would be gravitationally unstable. The star doesn't sit politely in the center, pulling the shell evenly. If the shell drifted even slightly off-center, the gravitational pull would be stronger on the near side, and the whole structure would be drawn in until it crashed into the star. There's no net gravitational force holding a uniform shell centered. It's balanced on a knife's edge. On top of that, no known material, nothing even theoretically possible, could withstand the unimaginable stresses of a solid object that big bridging across a star's gravity. A rigid Dyson shell would tear itself apart. So the Hollywood version, the solid ball you can walk around inside of, is the one version that genuinely won't work. So what would a real Dyson sphere look like? The answer is what Dyson actually proposed. Not a shell, but a swarm. This is the version physicists take seriously, called a Dyson swarm. Instead of one solid object, you build an enormous number of independent collectors. Think of them as gigantic solar panels or mirror satellites, each in its own stable orbit around the star. Millions, billions, eventually trillions of them, swirling around the sun in carefully arranged orbits like an artificial cloud. Each one captures a slice of sunlight and beams that energy where it's needed. Together, over time, they can be added to until they intercept nearly all of the star's light. No impossible materials, no instability, just an absurd number of orbiting pieces. The Dyson sphere isn't a ball. It's a swarm so dense it eventually shrouds the star. A swarm solves the stability problem, but it introduces its own headaches, and they're worth appreciating. With millions or billions of objects orbiting the same star, you have to choreograph their orbits so they don't collide. And at orbital speeds, a single collision could spray debris that smashes into other collectors, triggering a catastrophic chain reaction. You also have to get the captured energy from a collector to wherever it's needed, across vast distances, probably by beaming it as focused light or microwaves. Itself an enormous engineering feat, and the whole swarm has to be maintained forever, constantly repaired and replaced as units fail or drift. Building a Dyson swarm isn't a one-time construction project. It's the start of an eternal, solar system spanning active management. None of this is physically impossible, but it's a reminder that doesn't break the laws of physics and easy are very, very different things. There are other proposed variations on the theme, each solving the problem differently. There's the Dyson bubble, which uses ultralight collectors that act like solar sails, so light that the outward pressure of the star's own light pushes on them exactly hard enough to cancel gravity, letting them hover motionless in place rather than orbit. There's the Dyson net, a web of cables and collectors strung around the star. And at the far extreme of imagination, there's the Matryoshka brain, a Dyson swarm built not to house a civilization, but to run one. Nested shells of computers, each layer feeding on the waste heat of the layer inside it, turning an entire star's output into raw computation. A mind the size of a solar system. But the core practical idea remains the swarm. Many independent pieces gradually enclosing a star. That Matryoshka brain idea deserves a moment, because it points to something strange about where this logic leads. Named after Russian nesting dolls, it's a Dyson swarm of pure computers arranged in concentric layers. The innermost layer runs hot, powered directly by the star. It dumps its waste heat outward to a cooler layer, which runs its own computations on that leftover energy, and dumps its waste heat to a cooler layer still, and so on, squeezing every last drop of usefulness out of the star's energy before the final dregs radiate into space. A civilization that built one might not live in physical bodies at all. It might upload itself, existing as software running on a computer powered by an entire sun. It's speculative, but it raises a haunting thought. Maybe the most advanced civilizations aren't out there colonizing planets. Maybe they've turned their stars into thinking machines and gone quiet, lost in inner worlds we could never detect. And there's an even stranger variant. A Dyson sphere around a black hole. It sounds absurd. Black holes are famous for swallowing energy, not giving it. But black holes can be tremendous energy sources. Matter spiraling into one heats up and blazes with radiation before it falls in. A spinning black hole stores colossal rotational energy that could, in theory, be tapped. Some physicists have seriously proposed that a truly advanced civilization, late in the history of the universe, when stars have begun to die out, might cluster its collectors around a black hole as the ultimate long-term power source. The Dyson concept, it turns out, is more general than starlight. It's about wrapping any concentrated energy source to capture what it pours out. Okay, so a swarm of orbiting collectors. But the scale is the thing that breaks your brain. Where would you get enough material to build trillions of collectors big enough to wrap a star? Earth, the whole planet, wouldn't come close to providing enough raw material. And here's where the proposals get genuinely audacious. You take apart a planet. The favorite candidate for demolition is Mercury. Why Mercury? Several reasons. It's close to the sun, where the collectors need to go, and where sunlight is strongest. It's packed with useful materials like iron. And critically, it has low gravity, so it takes far less energy to lift mined material off its surface and into space than it would from Earth. The plan, sketched out by physicists like Stuart Armstrong, is a self-bootstrapping process driven by robots. You send automated miners to Mercury. They dig up material, launch it into orbit, and fabricate it into the first batch of solar collectors. Those first collectors generate energy, which you use to power more mining, more launching, more fabrication. Each generation of collectors builds the next, faster than the last. It's exponential growth. The swarm feeds on its own output, doubling and doubling again. Some estimates suggest that once the process really gets rolling, you could go from the first collector to a significant swarm in just a few decades. You'd literally disassemble a planet and reassemble it as a shell of power stations around the sun. Of course, in a few decades hides a colossal caveat. Completely taking apart a planet is a task almost beyond comprehension. Mercury is held together by its own gravity, with a binding energy so vast that fully dismantling it would itself require staggering amounts of energy and centuries, maybe millennia, of relentless work. The exponential math works beautifully on paper, but the early stages, building that very first self-sustaining foothold of miners and factories, is the hard part, the chicken and egg bottleneck. Still, the remarkable thing is that none of this requires breaking physics. It requires only patience, robotics, and time. It's an engineering problem, not a scientific impossibility. And that's exactly what makes it so tantalizing. It helps to picture just how thin and vast these collectors would be. Individual swarm units wouldn't be thick, heavy slabs. To cover the area needed, they'd have to be gossamer thin. Some proposals imagining sheets no thicker than household foil or even thinner. The reason is simple. The area to be covered is almost beyond comprehension. To surround the Sun at roughly the distance of Mercury's orbit, you'd need to tile a sphere with a surface area of something like the hundreds of quadrillions of square kilometers, vastly more than the surface of every planet in the solar system combined. There isn't nearly enough solid material in the inner solar system to build a thick shell at that size. The only way the numbers work at all is to spread the available matter into unimaginably thin films stretched across an unimaginably large area. So the real Dyson swarm isn't a wall of steel. It's more like a haze of countless impossibly thin mirrors, each catching its sliver of sunlight, together blotting out a star. So suppose a civilization does this. What do they get? Almost unimaginable power. That 4 followed by 26 zeros figure, the full output of a star, channeled to their purposes. What would anyone do with that much energy? The possibilities stretch the mind. They could run computation on a scale that makes every computer in human history look like an abacus, simulating entire universes, housing trillions of digital minds. They could power gigantic engines to launch ships to other stars, finally cracking interstellar travel. They could build vast new living spaces, habitats with more usable surface area than millions of Earths. A Dyson swarm isn't just a power plant. It's the foundation for a civilization that has, in a sense, outgrown planets entirely and become a creature of pure energy and engineering. But here's the part that brings it all back home. The reason scientists care about Dyson spheres beyond daydreaming. If they exist, we can find them. And the way we'd find one is beautifully simple, rooted in basic physics. The same insight Dyson had in 1960. It comes down to a law you can't cheat: the conservation of energy. If a swarm captures a star's light and a civilization uses that energy, the energy doesn't just vanish. The laws of thermodynamics demand that after you've used energy, you have to dump it back out as waste heat. Low-grade, leftover heat. Think of how the back of your refrigerator is warm, or how a busy data center glows with heat. A Dyson swarm would do the same thing on a stellar scale. So a star wrapped in a Dyson swarm would look very strange to our telescopes. Its normal visible light would be dimmed or even nearly gone, blocked by all those collectors. But it wouldn't be dark. Instead, it would glow brightly in the infrared, radiating all that captured energy back out as waste heat at longer wavelengths. A star that's too dim in visible light, but far too bright in infrared. That's the smoking gun. That's the signature Dyson told us to look for. Not a message, but the unavoidable thermodynamic exhaust of a civilization using its star. And the exact color of that infrared glow actually tells you something about the structure. A swarm sitting close to its star, like at Mercury's distance, would be heated to a certain temperature and would glow in one part of the infrared. A swarm built farther out would be cooler and glow at longer wavelengths. Most realistically, we'd be looking for partial Dyson spheres, swarms only fractionally complete, perhaps a civilization caught mid-construction, or one that simply never needed to enclose its whole star. A partial swarm gives a mixed signal. Some normal starlight still leaks through in the visible, alongside an unmistakable excess of infrared heat that shouldn't be there. That's actually the most promising thing to hunt for, because a fully completed sphere might be nearly invisible in visible light altogether. And a star that simply vanished from our visible catalogs but glowed in infrared would be deeply strange. The hunt, then, is really a hunt for stars with the wrong color balance. Too little visible light, too much heat, and no natural dust or debris that can explain it. And astronomers have genuinely searched for this. Using infrared space telescopes, missions with names like IRAS, WISE, and Spitzer, they've combed through data on huge numbers of stars, looking for that telltale excess of infrared heat without a natural explanation. There's even a second possible signature. If a partial swarm passes in front of its star from our viewpoint, it would block the starlight in odd, irregular ways that no planet could produce. And that brings us to the most famous maybe in this whole story. In 2015, the Kepler Space Telescope spotted the genuinely bizarre star, officially named KIC 8462852, but nicknamed Tabby's star after the astronomer Tabitha Boyajian who led its study. Its light did something no normal star does. It dimmed dramatically and erratically by as much as 22% in sudden, irregular dips. A planet passing in front of a star blocks maybe 1% and does so on a clean, repeating schedule. This was nothing like that. Huge, chaotic, unpredictable drops in brightness. And an astronomer named Jason Wright openly raised the possibility that everyone was thinking. Could this be an alien megastructure? A partial Dyson swarm under construction, passing in front of the star? For a while, Tabby's star was the most exciting object in the sky. The story captured the public imagination so completely that a crowd-funded campaign raised money to buy dedicated telescope time to watch the star closely, hoping to catch another dip in the act. Scientists scrambled to monitor it across every wavelength they could. It was a genuine moment when the question, "Are we alone?" felt, briefly, like it might be answered by a single weird star. But, and this is how science works, the megastructure idea has almost certainly not held up. When astronomers followed up with infrared telescopes, they did not find the strong waste heat glow that a real Dyson swarm should produce, and the dimming itself blocked blue light more than red light, which is exactly what you'd expect from clouds of fine dust, not from solid panels, which would block all colors equally. The leading explanation today is mundane by comparison. Uneven clouds of dust, perhaps from a shattered comet swarm or a disintegrating exomoon, drifting in front of the star, not aliens. But Tabby's star still matters enormously because it was a dress rehearsal. It showed astronomers exactly how to take the idea seriously, how to test it, and how nature usually turns out to be the answer. The hunt didn't stop there. In May 2024, a team running a survey called Project Hephaestos, led by researchers at Uppsala University, published the most systematic Dyson sphere search yet. They combed through roughly 5 million stars, combining data from the Gaia star mapping mission with 2 infrared surveys, hunting specifically for that mid-infrared excess a partial Dyson swarm would create. And out of those 5 million stars, they found 7 candidates. 7 small red dwarf stars showing exactly the kind of infrared glow you'd expect, with no obvious natural cause they could immediately identify. 7 possible Dyson spheres. It made headlines around the world. But once again, science applied the brakes. Within months, other researchers pushed back, proposing that the strange infrared signals were most likely contamination, the glow of distant, dust-shrouded galaxies sitting in the background behind those stars, fooling the survey. Several of the 7 candidates do appear to be explained this way. As of now, the mystery isn't fully solved. A few of the candidates still await a definitive explanation, and the honest scientific position is that the jury is still out. No confirmed Dyson sphere has ever been found. But the search is real, it's ongoing, and it's getting more sophisticated every year. It's worth understanding that these searches aren't random. They sit inside a deliberate framework. Astronomers have laid out systematic strategies for hunting waste heat from advanced civilizations across the galaxy, scanning huge infrared catalogs not just of individual stars, but of entire other galaxies. Because a civilization advanced enough could, in principle, wrap many stars, dimming a whole galaxy in visible light while making it blaze in the infrared. So far, surveys of large numbers of galaxies have turned up none that look obviously engineered. And that null result is itself meaningful. It feeds directly into one of the deepest puzzles in science, the Fermi paradox. The question of why, in a galaxy so old and so full of stars, we see no clear sign of anyone. If Dyson spheres are a natural stage for advanced civilizations, the galaxy should arguably be dotted with infrared glowing, visibly dimmed stars. We don't obviously see them. That absence is a clue. It might mean advanced civilizations are rare or non-existent. It might mean they don't build Dyson spheres. Or it might mean they build something subtler that we haven't learned to recognize. The empty-handed search is, in its own way, telling us something profound about our cosmic loneliness. So we should end on the big, skeptical question. Because even many scientists who study this are doubtful. Would an advanced civilization actually build a Dyson sphere at all? There are good reasons to wonder. Maybe a civilization advanced enough to dismantle planets would find more efficient, subtler ways to get energy that don't involve a star-sized construction project. Maybe they'd discover physics we can't imagine, new energy sources that make harvesting starlight look as quaint as burning wood. Maybe truly advanced minds simply don't need that much raw power, having turned inward toward efficiency rather than outward toward expansion. The very absence of obvious Dyson spheres in our searches so far is itself a kind of clue. It might mean they're rare, or that advanced civilizations don't build them, or that we're looking the wrong way, or, soberingly, that there's simply no one out there to build them. And yet the idea endures because it captures something profound. The Dyson sphere is what happens when you follow the logic of growth and energy to its ultimate conclusion. It's a monument to a civilization's ambition written across an entire solar system, in a form so large that it would be visible from other stars. We may never build one, we may never find one. But every time we point an infrared telescope at a strange, dim, heat-glowing star and ask, is someone there taking apart a sun? We're doing something extraordinary. We're searching not for a signal someone sent us, but for the literal fingerprints of an engineering project on the scale of a star. Somewhere out there, perhaps, a sun is flickering out invisible light and glowing in the infrared, slowly being wrapped in the works of a mind far older than ours. And if it is, sooner or later, we'll see it